Hello everyone, welcome to the 7th lecture in this series. I added this lecture intentionally to refresh you with the concepts of pointers and structures in C language as we enter into learning the next linear data structure, namely linked list abstract data type. So, here my special emphasis is to introduce you to the concepts which you might have learnt already learnt in C language with respect to dynamic memory allocation. As when we go for implementing a linked list, understanding of this concepts is essential. So, I wanted to give you introduction to pointers and structures and then to dynamic memory allocation before we enter into linked list. So, these are the contents of this lecture. I will be quickly introducing you or refreshing you the concepts of pointers, the concept of dynamic memory allocation. Then quickly we will have some slides on structures, how pointers and structures work together, and then I will be introducing you to self-referential structure, and then we have a simple linked list. That is the agenda of this presentation. So, pointers, I hope you may be learning the subject C in parallel. You know, pointer is a variable. The difference of pointer from other variable is that other variables hold values, whereas pointers hold addresses. You know, in computer, in memory, whatever we store is always associated with an address, which we call it as a memory address. And in data structures, when we study about a way of organizing data, be it storing data or retrieving data, we may have to deal from memory, and you know, every cell in memory has an address associated with it, and if in case we want to hold that address in some variable, then we may have to use this pointer variable. An advantage of pointers is that as we straight away deal with memory instead of dealing with variables, it greatly reduces the efforts on the part of your system, and it helps in increasing the execution speed. And apart from that, pointers have several advantages, as you can see listed it here. Like you can even call a variable or access a variable that is defined outside your function, provided you know the address of the variable, and then you can even use or pass and exchange values between functions with the help of addresses straightforwardly with the help of pointers, and it makes handling data efficient, and it at times even helps in minimizing the length of the code and also the complexity of the underlying program. So, these are the basic concepts with pointers. Consider that we have some statement like this: int xyz is equal to 50. You know, xyz is a variable of type integer with the value 50, and you can see that we have a pointer variable named p. How I say that it is a pointer is that we have a star prefixing it, which denotes that it is a pointer variable, and it is data type is int, which means it is an integer pointer. Once I make an assignment of this form like p is equal to ampersand xyz, which means I am taking the address of this variable xyz and assigning the same to the pointer. Thereby, I make the pointer p to hold the address of the variable xyz. So, internally this would be the state that we know this is the symbol table, or you can assume that to be a table with variable as xyz having a value of 50. And during the time we declare this variable, memory would be reserved for this variable xyz, and in our case its address is 1380, and as such because of this assignment, the address of this variable xyz is assigned to p, which means p now holds that value, as this is what you see here. And in turn p itself is a pointer variable, and so it should also have some memory address associated with it. In our case, that memory address is 2545, which we have put up here. So, what you understand here is that pointer is also a variable just like any other variable. So, for it also memory is allocated, and the speciality of pointer variable is that it can hold some memory addresses, and if you want a pointer to have the address of a variable, both its types should match. So here we have xyz to be an integer variable, and so its associated pointer should also be integer, that is mandatory here. And if we want to access the address of a variable, then I should use this ampersand operator. That is what we made use of in this assignment. In order to fetch the address of the variable xyz, I included this ampersand operator before it in order to retrieve its address, and once address is retrieved, I have put it up in this pointer variable. Similarly, we can use this ampersand operator for variety of other cases, like we can associate ampersand with some variable, we can associate ampersand with some array element, etc., in order to fetch its respective addresses. And of course, there are certain illegal usages as well with respect to this ampersand operator. Like I cannot associate ampersand with the constant like this, ampersand 235 is invalid, and I cannot associate ampersand with an expression, and I cannot associate ampersand with an array name. And then we need to know how we declare and initialize pointers. You know very well, in order to declare a pointer, I should give it an associated data type and then a suitable name. And these once a pointer has been declared, then we may have to initialize the pointer with some value. So here in this case, I have initialized this pointer p to hold the address of the variable xyz. If I do not make this assignment, then it means the pointer is left uninitialized and it may be holding a null value or nothing. And these are some things which you should remember when you make use of pointers. Like pointer variables must always point to a data item of the same type. This is one I mentioned before, that if you are using making an integer pointer, it can point to some integer variable, and we cannot mix and match because that will lead to some erroneous output. So here in this example, you could see that we have a variable x which is of floating point type. We have declared a pointer p which is of type integer, and it is wrong that we make an assignment of this kind, that is I store the address of a floating point variable to an integer variable, which is of course forbidden. And the second thing you should remember is that assigning an absolute address to a pointer is prohibited. Here we have an integer pointer named count, and I cannot assign some value straightforwardly to that integer pointer. I can assign only the address of some other integer variable to this pointer count with the help of referencing operator like ampersand, and not like this. And apart from that, you need to know about null pointer, which means it points to nothing. That is also we will be using in linked list. So, I wanted you to be aware of it. And then how to access a variable through its pointer. And whenever we make use of pointers, in order to access a variable through a pointer, we can use this operator called indirection operator, which is denoted by star. So, here you see we have two variables a and b and an integer pointer p, and we make pointer p to point to the address of the variable a, and here I am actually fetching the value of a through the pointer p which is pointing to it. So, in order to access the value held in a with the help of this pointer p, I use this indirection operator before it. Now, it fetches the value held in this address, which is the address is the address of a. The value held in that address is actually the value held in a, which is assigned to b now. So, the same thing I have shown here with an example program. Here you could see that this assignment statement a equal to 4 into c plus 5, where c is an integer variable having a value of 5. So, this would happen as usual. So, here in this statement you could see that in this assignment b is equal to 4 star p plus 5, where we actually look at the value held in the address by p. Actually, p holds the address of c as per this assignment, and the value held in c is 5, which is actually fetched here with the help of this indirection operator. And there are certain other facts which you need to know with respect to C language, and that too with respect to pointers. You can add an integer to a pointer, that is allowed. You can subtract an integer from a pointer, and then you can subtract one pointer from another provided it is related. And if both P1 and P2 are pointers to the same array, then if we subtract those two pointers, it will give you actually the number of elements available between those two set positions in which the pointers are pointing to. And there are certain other things which are not allowed. You can't add two pointers like this, and you can't multiply or divide a pointer in an expression of this kind. And whenever, if you have a pointer, and in our case let us imagine that pointer to be an integer pointer, and if in case I increment a pointer, in that case the pointer will get incremented by 4 every time, which means for integers the system has reserved me 4 bytes each, and every time I increment pointer value by 1, automatically the pointer will move by 4 bytes every time, which is actually the scale factor with respect to integer. And of course, for different data types the scale factor would be different, and accordingly incrementing the pointer by 1 will take you or move you by that scale factor. Now we move on to the next concept, which is memory allocation. Whenever we take a program for execution, the program should be available in memory. And when we take a program for execution, you do two steps before. You write a program, you compile, and once compilation is successful, you have the equivalent object code or the machine code, and that machine code gets loaded into your memory. And apart from that, there will be certain portion of memory reserved for certain other things which are associated with your program, namely space for variables, space for constants, and we have certain portion in memory called data stack and certain portion in memory called data heap. And the memory assigned for holding the object code as well as for holding variables and constants is not going to change. Whereas when we think of the memory associated with stack and heap, they are going to be varying during the run of the program. So we have certain portion on memory for the particular program to accommodate the stack as well as the heap, and the portion of stack is of course reserved for handling function calls, and this heap portion is actually reserved for handling dynamic memory allocation. So this is portion of memory that will get allocated during runtime, and this portion of memory may shrink and expand during the running time of a program. So as you see here, the portion corresponding to instructions and variables are going to be the permanent storage area, and of course the portion corresponding to stack and heap are going to get expanded and shrunk during the run of the program. And as I said before, the portion pertaining to heap and stack may expand and shrink. We call those portion as part of dynamic memory allocation, and in order to support dynamic memory allocation we have certain functions, and here is the list of functions which do support this dynamic memory allocation concept. One is malloc, which is a function used to request your system for certain portion of bytes, and as soon as if memory allocation turns out to be successful, a pointer to that allocated memory will be returned. And calloc is a function which is also for allocating space for certain amount of bytes or certain array of elements, and once calloc turns out to be successful, that is memory allocation turns out to be successful, then all those allocations will be initialized to 0. So that is the difference of malloc and calloc. With malloc we will be just allocating portion of memory as requested, and once allocation is successful a pointer will be returned, whereas in case of calloc a pointer will also be returned. In addition, whatever spaces that has been allocated as a part of this dynamic memory allocation will be initialized to 0. And we have a function named free of, and its purpose is to free up the space that has been allocated earlier. The very advantage of dynamic memory allocation is that here we can request for additional space whenever there is a need, and whenever we don't want that memory location, we can free up that space with the help of free of function. So here is where it contradicts with the static data structure which we learned before, especially arrays. And I was mentioning when we were learning arrays, that with arrays I cannot either expand or shrink its size, whereas with the help of this dynamic memory allocation, it is possible to expand and shrink as and when we need. And we have one more function named realloc. Here its purpose is to modify the size of already allocated space. So if suppose we had already allocated some space with the help of malloc or calloc, and if suppose we want to further either increase or shrink the space that has been allocated already, then we can go with a realloc function for that purpose. So here this is the syntax for allocating a block of memory at runtime. We may have to make a call to this function malloc. Of course, we need to specify how many bytes, how many number of elements we want, and what would be the size of every element. If in case I want to allocate 100 elements of type integer, then I need to estimate the size reserved for integer with that particular system with the help of size of function. It will return me the number of bytes the system would allocate for every integer, and I want the system to allocate integers, 100 elements of type integer. So now memory allocation would happen, and once memory allocation turns out to be successful, I want a pointer to be returned. Since all these elements are of type integer, I want that pointer to be of type integer, and that is what we dictate here, or we make an explicit type conversion here for the pointer, and we name that pointer to be p here. So the possibility is that either this call to malloc may turn out to be successful or unsuccessful. Here, as we have requested for 100 elements of type integer, it would be successful only if there is enough memory to accommodate 100 elements of type integer contiguously or consecutively. Otherwise, it turned out to be a failure, and our malloc function would return a value of null. So here in this example, we have requested for 100 elements of type integer. So altogether it would be turn out to be 100 into 4, which is 400 bytes. And if malloc turns out to be successful, then 400 bytes would be reserved in memory, and we will have a pointer p pointing to that starting of that memory location. And this is how we release the used space. So whenever we feel that the memory which we had allocated earlier with malloc is no longer required, we can make a call to the function free of and passing the pointer associated pointer with respect to malloc there. So in our case, if we have already allocated memory with the malloc function and p is the pointer pointing to it, then we may have to specify free of p here. And the next function is how to alter the size of the block which we have allocated already during runtime with the help of malloc. Imagine that we have allocated already with the malloc function, and ptr is the pointer pointing to it. And if suppose we may either want to expand the size of the block or to shrink the size of the block, then we have to make a call to this function realloc and passing the same pointer ptr as an argument, and we may have to specify the new size. So now realloc has to either expand or shrink the size depending upon our requirement, and if in case if it has to expand the size, then we will be checking for we will be making a check, the system will be making a check whether the additional requirement which we have made is available at the same contiguous location. If so, it will allocate the additional memory and the same pointer will be returned. If not, system will make an attempt to move the entire data block to some other region, and it will ensure that whatever we had with the whatever data we had with our old block is also preserved there. And if suppose if we have asked for some bigger size to be allocated, and if suppose there is no space with the system, it may return a null value at the end. And we have one more function called CLOC, which I said before. Its purpose is to allocate memory and also to initialize all the allocated spaces to 0. So here we have I have mentioned here for example sake that we could use size underscore t as a data type. It is a special type which is used to denote unsigned integer. And if suppose we do not know the space reserved for every data type, then it is always safe to use the size of operator there as we did before. And you need to know by this time that every time we ask for memory to be allocated dynamically, it is always allocated from the heap portion, data heap portion. And here in this case I have asked for n number of elements of type size e size, and so that much amount of space will be allocated in the data heap portion in main memory. And if CLOC turns out to be successful, a pointer to the first byte of this memory will be returned. And if suppose CLOC turns out to be unsuccessful, then the pointer will be holding a value of null. So, just by reading the pointer as whether it is holding some address or null, we will be knowing whether memory allocation had been successful or not. So, having learnt dynamic memory allocation, now we move on to the next topic, which is structures. You know, with the help of structures, it is possible to logically group items of different data types together. At times it is essential for us to group together heterogeneous data items, and in such cases we can very well go ahead with structures. In order to define a structure, you need to use the keyword struct followed by some name for that structure, and within that you can specify members for that structure. You could have n number of members, each of different types, and you can put together within a structure. And you need to remember that within the structure, members should have different names and they should be distinct from one another. And once we have defined a structure, then we may have to declare variables for this structure. For declaring sake, we need to specify the struct keyword, its name, and followed by that as many variables we want to have. So, now every variable will be of this structure type, and in order to access a structure, we will be using the dot operator. We need to mention the structure variable followed by the member name. So, variable dot member is the syntax used for accessing any values from the structure. And there are certain other facts which you should know about structure. You could assign one structure to another structure. Say for here, if A1 and A2 are of the same type of structure, then we can very well assign one structure variable to another structure variable. Of course, this is not possible with respect to arrays, whereas with the help of structures, it is possible to assign one structure variable to another, provided they are of the same type. And then there is one another thing which you should know about structures, that we cannot compare two structure variables for equality. Like this we cannot do. And then about pointers and structures. So, here we have already seen how to declare a structure and to create variables for a structure. Here is one example where you could see that I have an array of structures. Class 100 means I am creating an array of structures for this structure named student, and you could see that I have another pointer variable which is also a variable for this structure. So, here in this case what we do is we have this array of structures class, and when I merely say class, it means I refer to the 0th element of this array of structures, which is class of 0. And here we have a pointer named ptr. it is also pointing to data objects of this structure named student. So, if suppose I make an assignment of this form pointer is equal to class, then it means that we have a pointer PTR which is pointing to the 0th member of this array of structures, which is class of 0. So, pointer will be holding the address of class of 0 when we make an assignment of this form. So, whenever I make an attempt to increment this pointer by 1, as I said before, we talked about scale factor, right. Here now the pointer is of type structure. So, every time I increment pointer by 1, the pointer will automatically get incremented by the size of this structure named student. So, thereby this structure actually has 3 members, namely roll number, department code and the CGPA. The name of the structure is student. So, for every student we will have a roll number, a code and a CGPA. So, that makes up a record of a student, right. So, whenever I increment pointer by 1, it means I move to the next student record. So, the next thing which you should know here is that whenever we have a pointer variable and to a structure, we can access the structure's members by the arrow operator instead of dot operator. So, here in order to access the members of the structure with this pointer PTR, in order to refer to each of its members like roll number, code and CGPA, I can use arrow operator with it. So, that helps me to deal with this members straight away with the help of pointers. The next thing which I wanted to emphasize here is with respect to self-referential structures. What self-referential structures actually mean? So, here you can see an example where we have a structure named list. There are 2 members for this structure named list. One is a member named data of type integer and another one is the speciality here. We have a pointer named next and the type of this pointer is that of the same structure. The data type of this pointer is that of the same structure. So, here what we do is that we have one of the members of the structure which is a pointer and the pointer's type is that of the same as that of the structure itself. We call such a structure as a self-referential structure where one member is a pointer and its type is that of the same structure. Such a structure we call it as a self-referential structure. And here how this structure would look like in memory is that we will have 2 fields, one is data and another one is next, and the type of this next field is that it is also a structure. So, we can make this next pointer next to point to another element of this structure type. So, we say that it is a self-referential structure. So, it is the concept of self-referential structures which we will be using for implementing the linked list, and that is why I wanted to emphasize I wanted you to be very clear with self-referential structures. So, here as an example for the list which we learned before, that is we have defined a structure named list having 2 members. One is a member named data of type integer and another one is a pointer of type list, right. So, here what I do is for that structure named list I create 3 variables named A, B and C. Now, since A, B and C are members or variables of type struct list, every variable here will have 2 fields, namely data and next. Now, I assign values to every member of these variables A, B and C. For every variable it has a data value and a next value. So, in order to access respective members we use this dot operator, A dot data, B dot data, A dot next, B dot next, etc. And I am assigning values of 1, 2 and 3 for the data of A, B and C, and all the next values I am assigning it to be null. So, this will be the state. A will be 1 having a value of 1 and its next would be null. B would be having a value of 2 and its next would be null, and similarly C would be having a value of 3 and its next would be null. If suppose I want to put these 3 variables in sequence, or I want to chain all these variables together, then I could do that simply with the help of assignments of this form. So what I do is that instead of having a dot next to be null, I just make a dot next to have the value of B, or to have the address of B. By making this assignment, automatically a chain gets created, that is A and B will now become a sequence with A containing the address of B. And similarly, I can make B to have the address of C by making assignment of the form B dot next is equal to ampersand C, which is address of C being put up in the next part of B. So once I do these two assignments, then automatically that gets that creates a chain for me with A, B and C forming up a list. So this is the principle behind linked list, the concept of self-referential structures, which we will be using during the implementation of linked list. Now if I ask you what is available in A dot next arrow data, it means A dot next is this portion. This portion is pointing to the the variable B, and what is available in B's data part is 2, that would be returned as the result. Similarly, if I ask you A dot next arrow arrow data, then that would be the value of 3. So this is the concept of self-referential structures, and here you see an illustration where we have 3 members, roll number, name and age, and we have one self-referential structure named next. So with the assignments of this form, that n1 dot next is ampersand n2 and n2 dot next is equal to ampersand n3 and n3 dot next is equal to null, we actually chain up these 3 nodes n1, n2 and n3, and this is how we actually create links between different records, or we are going to create a linked list in practice. So to summarize what we have learnt so far, we have learnt what pointer variables are. Pointer variables are like any other variable in any other variable, they will be holding the address of some other variables, and for a pointer variable to hold the address of some other variable, both their data types should match. And then we learnt with structures we can bring together items of different data types together. And then we learnt with the concept of dynamic memory allocation, we can allocate at runtime whatever memory we need with the help of functions like calloc and malloc, and whenever we make a call to such functions, memory is reserved from the data heap portion, and whenever we don't want that memory, we can free up the space with the help of free of function. Then we learnt what pointers and pointers to structures are. And then finally we learned the concept of self-referential structures, whereby we can bring in we can link or chain up variables or records together, and this provides a way for us to implement linked lists, which we will be learning in detail with the next presentation. Hope you would have understand the concepts better, and